Welcome to the second lecture of week 4, and in this lecture we will discuss design of support. Discussion on design of support we have started from the previous lecture, and where we have discussed what are supports for vertical as well as horizontal vessel, and there we have also discussed one support, that is bracket or lug support, which is used for vertical vessels of a small height. Now in this lecture we will discuss design of support, and here we will discuss design of support for horizontal vessel, and that is the saddle support. So let us start the discussion on saddle support. So general practice of supporting horizontal cylindrical vessel is by means of saddle support, and number of support or number of saddle may be 2 or more. So basically this saddle support is used for horizontal vessels, and how it looks like that we can see from these images. So if you see this image, here we have the horizontal vessel, horizontal cylindrical vessel, okay. Different sections you can identify, this is the shell, this is head, and it is basically supported by these supports, and these supports are called as saddle support. Okay. So if you see, saddle support is nothing but this structure, okay, and which has curvature, and that curvature fits well with the cylindrical vessel. If I want to see separately the saddle support, that you can see in this image, and where this is basically the saddle, and where this curvature will depend on the diameter of vessel. Okay. So this is basically the saddle support. Now if you focus on this image, here we have horizontal vessel, and as far as stresses are concerned, this horizontal vessel has longitudinal stress as well as circumferential stresses. Okay. So this saddle support should be designed in such a way so that it can withstand, or it can hold the vessel with all longitudinal as well as circumferential stresses. So from here onward we will discuss the stress analysis related to the saddle, and according to these stresses what should be the condition that must be satisfied for completing the designing of saddle. So let us start the stress analysis for saddle. So as far as stress analysis of saddle is concerned, we will first discuss the longitudinal stresses, and then we will focus on circumferential stresses. Now as far as longitudinal stresses are concerned, we will first speak on longitudinal bending moment, and then that moment will be considered to compute stresses in longitudinal direction. So let us start the discussion on longitudinal bending moment. And further we can see that these longitudinal stresses are available in shell. So whatever stresses are available in shell, that should be supported by saddle. Okay. So in this case, as far as longitudinal bending moment is concerned, we consider that, or we focus that discussion on shell. Okay. So if you consider, here I am having this shell which is horizontally placed. If you see, this is the shell, and where it is lie on two saddle, that is this one as well as this one. Now the total weight of this shell will be supported by these saddles, and that will be taken by these saddles. Now as far as weight is concerned, what that can be, that includes the weight of shell, weight of head, and whatever content is inside the vessel, that its weight should be added to that. And if I am having different attachment inside this, for example if I am having tubes or some other assembly, so weight of those assembly will also be included in total weight. Okay. So here we can see the total weight, and that total weight will be equally distributed to two saddles, or if I am using 3 saddles, so that will be distributed equally to 3 saddles. Okay. So for example if I am having 2 saddle and total weight will be transferred to these 2 saddles equally, I can make the moment diagram. Okay. Now to make the moment diagram, it will be easy when we consider that it will be easier to consider shell as a beam which is lie on 2 supports. Okay. Now, if I am having a beam which is lying on two support, how I can make the moment diagram, that we will discuss here. So, for example, this is a beam which is lie on this saddle as well as this saddle. Now, what happens, total weight will be equally divided in these two saddles. Now, what happens when the weight will act to these support, the support will give the reaction in opposite direction. So, this will happen here and it will happen on second support also. Now, for drawing the moment diagram, what we can consider that, for example, if this is the beam, okay, and you must understand that moment diagram we prepare from left to right, when we analyze the system from left to right. So, what we have considered over here, that shell is considered as a beam which is supported on two saddle. Okay. So, as we have discussed that when weight is falling on the saddle, saddle will give a reaction in opposite direction. So, for example, if I am having this beam, or that you can consider as a shell, which is we are considering as beam. Now, this beam is basically supported at two places. This is one saddle, this is another saddle. So, this is one saddle, this is second saddle. Now, what happens when this saddle reacts upward, and this saddle will also reacts upward, okay, and total weight of this shell will lie at the center. Okay. So, here I am having two reactions, and at the center I am having total load of the shell. So, when I am starting drawing the moment diagram, I will start from left to right. So, when I am starting from left, the first reaction will occur due to first saddle, and it is moving in upward direction. Okay. So, it will try to turn this beam towards anti-clockwise direction. I hope you are getting me. So, when I am moving from left to right, the first load will the first reaction will be due to the beam, and it will, and as it is moving upward, it will try to revolve it or move it in anti-clockwise direction. And further, the second load I am having from this is the load at the middle of the beam, that is the load of the shell. Okay. Now, this load of the shell is acting downward. So, it will try to make, or it will try to rotate this beam in clockwise direction. Okay. And in the similar line, if I keep on moving from here towards the end, second saddle will give the reaction in upward direction, and it will revolve the beam in anti-clockwise direction. So, when we draw the moment diagram, what happens, whatever anti-clockwise movement, that are denoted by minus sign, and whatever clockwise moments, those are denoted by plus sign, that is the normal consideration. So, the moments which are causing through saddle support, these will be denoted by minus sign, and whatever will be created by weight of shell itself at the center of beam, it will be denoted by plus sign. So, considering this, if I am focusing on this moment diagram, this M2 and this M2 will be negative, however, this M1 would be positive based on discussion we have just done. Now, further, if we consider this assembly, if you consider here, what is this A? A is basically the distance at middle of the saddle from end of the shell, from this side as well as from this side. Okay. And then this capital H is basically the height of domed section, and L is the tangent to tangent length. Tangent to tangent length we have already discussed in previous lectures, because this head is basically making tangent to the shell, and therefore, it is called tangent to tangent length. If we consider cross sectional view of this assembly, here you can see R is the inner diameter of vessel, theta is the angle which is made by support to the center of vessel. Okay. So, this is minimum angle of this support is 120 and then it keeps on moving, and when support is attached to the shell, this section we call as horn of the saddle. Okay. So, as far as bending moment diagram, M1 would be positive and M2 would be negative. So, at mid span if I am considering, it means I am considering the center part of this where M1 will play its role and M1 will have the positive sign, and that would be denoted by this, which is equal to W1 L by 4, where W1 is the weight on each saddle, and bracket 1 plus 2 R square minus H square by L square divided by 1 plus 4 H by 3 L and minus 4 A by L. So, this is basically the moment at mid span. At support, if I am considering where I am having M2, and this is basically denoted by negative sign. Why it is, that we have already discussed, and it is equal to minus W1 A 1 minus A by L plus R square minus H square by 2 A L divided by 1 minus 4 H by 3 L. So, these two expression of longitudinal moment we have considered, which will be used for computation of longitudinal stress in shell. So, here I am having longitudinal bending stress in shell. So, here we have seen that longitudinal moments are occurring at two different places, at mid span as well as at support. So, if I am considering mid span will have two section. If this is the vessel, mid span would be at the middle of this total length, and it has two section. First is at the top and second is at the bottom. Top, it means top section or top point of top point at middle of the vessel, and bottom section we are considering at the center or the middle point of the shell at bottom. So, stress at the top is given by F1, which is equal to P r by 2t minus M1 by pi r square into t. Okay. And at the bottom we will calculate F1 dash as a longitudinal stress, and that is given by this expression. So, here you see we have at the bottom plus sign and at the top we have minus sign. So, stress at the bottom would be maximum. Now, we have longitudinal bending stress at saddle. It means wherever I am having the support, again this saddle will include 2 points. First is at the top of it and second is at the bottom of it. So, at the top if I am considering, it means I am considering top of shell which is just above the saddle. Okay. And bottom if I am considering, it means bottom of shell which is attached to the saddle. Okay. So, here basically we are discussing these stresses in shell only. Therefore, all top and bottom are considered in shell only, whether it is lying in saddle or whether it is lying away from the saddle. Okay. So, when I am having longitudinal bending stress at the saddle, at top we compute that in terms of F2, which is equal to P r by 2t minus M2 by K1 pi r square into t, and at the bottom we have this F2 dash where I am having constant K2. So, this K1 and K2 are design constants which will be discussed later. So, for satisfactory design, all these stresses, that is F1, F1 dash, F2, F2 dash, all these stresses should be less than or equal to Fj, okay, where F is the allowable stress of shell. So, in this way we calculate stress in shell in longitudinal direction. Now, we will discuss stress in circumferential direction. So, when I am considering circumferential stresses, it means throughout the circumference stress will form, and which we have also discussed as hoop stress. Okay. So, whatever stresses are forming in a shell, all these stresses will be supported by saddle only. Okay. So, due to shear, all these stresses would be transferred to saddle only. So, here we are considering two sections. First is tangential shearing stress, which is for unsupported part. Unsupported part means where saddle is not occurring or saddle is not available. And second, we will consider circumferential stresses, which is just at the support or at the saddle. So, let us start that discussion with tangential shearing stress, which is related to unsupported part of vessel. Now, load is transferred from unsupported part of the shell to part over the supports by tangential shearing stress that we have discussed already, which vary with the local stiffness of shell. What is the meaning of that local stiffness? For example, if I am providing some structural support to the cylinder or to the vessel, the load will be transferred, or the circumferential stress will also be transferred to that structure. Okay. So, in that case, what we can consider, if I am having this much length and then I am having here head. So, head is basically attached to the shell by welding. Okay. So, that welding will provide structural strength to that support. Okay. So, unsupported part in that case would be which is away from that edge where head is connected to the shell and which is not available at saddle. So, whatever that part we have, that we will consider as unsupported part. So, here I am having case 1 where A is greater than R by 2. Now, what is A? A, if you remember, we have discussed earlier that it is the distance from edge of shell to the middle point of the nearby saddle. So, if that distance A is greater than R by 2, which is basically internal diameter of shell, if that distance is greater than R by 2, we can calculate maximum tangential shearing stress as given by this expression, where Q is the maximum tangential shearing stress equal to K3W1 by RT bracket L minus 2A minus H by L plus H. So, all this L, H, A and R, T, all these parameters you know. Now, what is this T that appears in F1 and F2 expression also? This T is basically the minimum thickness of shell, because we are discussing stresses in shell. Okay. So, here we have this design constant K3 that we will discuss further along with K1 and K2. Now, second case I am having, if A is less than R by 2, it means if that saddle is close to the end or close to the head. So, in that case I am having two section. So, when A is less than R by 2, it means the saddle is close to the end, and at that point we will consider stress in shell as well as that in head. So, here we have two sections, shell as well as head. So, in shell we can calculate shearing stress as K3W1 by R2 as it is shown here, where Q should be less than or equal to 0.8 F. Okay. Now, this condition will be applicable for this expression also and for this expression also, because in both cases we have Q. Now, in the end or in the head we have stress as QE, which is equal to K4W1 by RTE, where TE is the minimum thickness of head and K4 is again the design constant that we will discuss later on. Now, condition to be satisfied this QE is it should be less than equal to 1.15 F minus Fn, where Fn is denoted by this PDOC by 2T. Okay. And this C is basically the shape factor. If you remember that shape factor we have discussed in design of heads. For different types of head we have different methods to compute this shape factors. So, this shape factor will be computed based on procedure whatever we have already discussed. Okay. So, in this way we will calculate tangential shearing stresses in shell as well as in head. Now, next point I am having is the circumferential stresses, and these stresses are falling in shell which is just above the saddle. Okay. So, this is basically we can call as supported part. So, at the support at lowest point of cross section, we can calculate stress as F3, which is equal to K5W1 by T bracket B plus 10T, and that should be equal to 0.5 into yield point stress. And at the horn of the saddle, what is that at horn of the saddle, where horn is where edge of horn is appearing in shell. So, that is basically the end of support in shell. So, there we have circumferential stress as F4, which is equal to minus W1 by 4T B plus 10T minus 3 K6W1 by 2T square, and this expression we will use if L by R is greater than 8. And in the similar line, if L by R is less than 8, we will calculate F4 from this expression. Now, what is this B plus 10T? If you see this image here, this B plus 10T is appearing. B is the total width of the saddle and T is the thickness of shell. So, B plus 10T is this section. Now, what is this section? It happens that when we weld the saddle, okay, when we weld the saddle to the shell, wherever that welding occur, it makes the shell weaker at that particular point. So, for that purpose we provide a reinforcement strip of width B plus 10T. Okay. So, sometimes we provide it if thickness of the shell is not significant, and if it is significant we do not provide that reinforced strip. Okay. So, that B plus 10T is nothing but the width of reinforced strip, and all these circumferential stresses should be satisfied or should be falling less than or equal to 1.25 F. So, in this way we will consider different stresses and their conditions to be satisfied. If saddle is designed very well, all these conditions must be satisfied. So, till now we have discussed stresses which are falling in shell due to shell. Now, we will discuss design of saddle, because whatever stresses are occurring in shell or whatever forces are applied in metal sheet of vessel or the weight of vessel itself, that should be withstand by the support. So, support should also be strong enough to bear all these loads. So, for that purpose we have to satisfy the design equation which is related to saddle. So, let us discuss that. So, saddle should be strong enough to withstand the forces imposed by vessel. Okay. And for that purpose we have a design equation, and that is basically horizontal component of all radial load which are falling on saddle, that should be F, which is equal to K9 into W1. Now, if you focus on this image, here we have this saddle support with reinforcement plate, and here we have this cross sectional view. Now, if you consider this force, it means that force, the horizontal component of radial forces, that would be F, which is equal to K9 into W1. So, when I am having a saddle, okay, and when failure will occur, it will fall either in one direction or like this or like this. Okay. So, in that sense or in that way, we should consider horizontal component of all radial forces together, and then we will apply the stress condition. So, total horizontal component of all forces will be given as F, and that would be K9 into W1 as it is shown here, and that should be F, and F divided by R by 3 into B, that should be less than or equal to 2 by 3 F. Now, this F is basically horizontal component and this is the acting area. Now, why it is acting area? If you consider this image, here we have this distance or this length R by 3. R is basically inner diameter of vessel, and its 1/3 part would be this height into B. Okay. So, what is B? B is basically the width of saddle. So, this is basically the acting area for F. So, F divided by R by 3 into B, that should be less than or equal to 2 by 3 F, where this F is the allowable stress of saddle material. So, in this way we consider all stresses in shell which is due to internal pressure or design pressure and due to saddle, and further we have checked the strength of the saddle. Now, whatever design equation I have considered in this lecture, it includes some design constants like K1, K2 like that up to K9. So, what are the values of these constants that we can see from this slide. So, let us discuss that. Here we have values of constant for saddle support. So, here we have contact angle, that is 120 is the minimum angle and 122, and we have long table which I will show further, and here we have K1, K2 for different conditions like A is less than R by 2 or other condition, and then K3 when shell is stiffened by end of the vessel, and we have other conditions also, and similarly K5, K6, K7, K8 and K9. So, here you see values are available at 120 and 122, and further we have the table from 122 to 158, we have different values for these constants. Now, we have values of all these constants from 160 to 180. So, here you can see that contact angle of the saddle to the shell vary from 120 to 180. And now we will discuss different dimensions related to saddle, and that can be better understood by these diagrams which are shown over here. If you see this image, here we have the vessel diameter of 1.2 meter or lesser than that. Now, what would be the standard dimension? Dimension includes this J, E, C, G, Y, T, B, P, that is the thickness of bearing plate. All these parameters have standard dimensions. In the similar line, when vessel diameter exceeds 1.2 meter, in that case all these parameters whatever are shown in this image, these are summarized over here. Like here we have vessel diameter and then maximum operating weight, V, Y, C, all these dimensions which are available in previous images are summarized or shown in this table, and similarly other parameters also. So, these are standard dimension used for design of saddle. Now, we will see a few examples for support design. So, here I am having example 1, and in this example the cylindrical vessel of 3 meter outside diameter and 8 meter length is supported by 4 lugs. So, this example is basically related to bracket or lug support which we have discussed in last lecture. So, the vessel is filled with the liquid or fluid having density 870 kg per meter cube up to 5 meter height and is being operated at 1.5 mega Newton per meter square in gauge. It is covered with flat head from both end having 12 kilonewton of each head. Corrosion allowance is 2 mm and it is class 2 vessel with double welded butt joint with full penetration, and vessel is made with IS 2041 1962 20 molybdenum 55 material and its design temperature is 450. Wind pressure on the vessel is 0.9 kilonewton per meter square. Height of the vessel from foundation is 1. So, total height of the vessel is 8 and height from the foundation is 1. So, from foundation total height of vessel should be 9 meter. So, height of bracket from foundation is 5 meter. So, this is basically length of the column. End diameter of anchor bolt 3.1 meter and steel channels are used to support the lugs. Now, here we are given allowable stresses of horizontal base and gusset plate, that is 100 mega Newton per meter square, allowable stress of channel 150 mega Newton per meter square, density of shell material and mu are given as this and this respectively. What I need to find is standard thickness of the shell. Then I need to compute the minimum thickness of horizontal and gusset plates for this dimension, and we have to find out the area of cross section of channel column for section modulus of column as 200 centimeter cube. Okay. Also we need to suggest the suitable column. So, here I am having different parameters where operating pressure and all other parameters are given which we have discussed in the problem itself, and let's start the solution of that. The first part is I need to find out standard thickness of shell. Okay. Now, if you consider this problem, it has operating pressure as 1.5 meganewton per meter square and liquid is available up to 5 meter height. It means it has static load of liquid also. Okay. So, when this type of condition is there, when I am having operating pressure as well as static head of the liquid, I have to compute the design pressure in slightly different way. For that, first of all I have to find static load of the liquid, that is rho GH of the liquid, and then I have to compare that with condition. Now, condition is when that load is greater than 5% of operating pressure, I will add static head with the operating pressure to compute design pressure. Otherwise, if it is lesser than 5%, I will consider 5% extra as design pressure as we usually do. So, static head would be rho GH and that can be found as 42673.5 Newton per meter square, and which is equal to this much mega Newton. And when we consider 5% of 1.5 mega Newton per meter square, it comes out as this, and as this value is lesser than this, I will consider design pressure as 5% extra than operating pressure in gauge. So, here we have this is the design pressure, and further calculation is similar as we have discussed in previous lectures for design of shell. So, this is the minimum thickness of shell by standard expression. Adding corrosion, it gives 28.24 mm thickness, and then standard is available at 32 in table B1. So, standard thickness of shell is 32 mm. Now, I need to find out thickness of horizontal as well as gusset plates. For that case, if you consider this is the expression to find out thickness of horizontal plate, okay, and to compute this I need to calculate PAV first, and for calculation of PAV I need to find out total load on each lug, okay, and that is given by this particular expression. In this expression we need to find out PW. H minus HC is the total height of the vessel, which is basically 8 meter, N is the number of lugs and C is the anchor diameter. W max is the maximum weight of shell and accessories. So, first of all I need to compute PW and W max so that I can find out value of P. So, PW is coming as 17.01, which can be computed as 0.7 into 1, that is K1 K2 if you remember. This is the expression K1 K2, K1 0.7 for cylindrical vessel, K2 will be 1, and P1 which is the wind pressure, it is given as 0.9, and then H1 is the total height of vessel from foundation and that is 9, DO outer diameter of vessel, that is 3. Considering all these value we can find PW like this. Standard thickness of shell is given as 32 mm, and then we need to find out maximum weight of vessel. Now, how I can find out maximum weight of vessel? It includes weight of shell, weight of head and weight of internal attachment. In this case internal attachments are not given, but liquid is given up to 5 meter height. However, for maximum weight we consider maximum possible situation, and that could be when vessel is completely filled with the liquid. Okay. So, here we will consider weight of shell, weight of head plus weight of liquid when it is completely filled in the vessel. So, to compute this, first of all we have to find out weight of shell. How I can find out that? That is given by this expression pi DO minus TS, that is standard thickness of shell. This is basically for average diameter. So, that is periphery into TS is the area into total length, that is 8 meter, and then this basically gives the volume into density of material of shell and then G, it will give value 177.87. Weight of head 12, because one head includes 12 kilonewton, so it comes accordingly. Weight of liquid, how I can find weight of liquid? That would be the internal volume of the vessel, that is pi by 4 dO square minus di square into L into rho, that is density of liquid, into G. So, considering those parameters, you can calculate weight of liquid, which comes out as 462.02. And similarly, I can find out maximum weight. Once I am having maximum weight, I can find P as this. Now, once I am having P, I can calculate PAV and then THP, that is the thickness of horizontal plate, and which comes out as 27.10 m. I am not adding corrosion to this because it is not coming in contact with the liquid. So, directly next value available in table B1, that I can choose as horizontal plate thickness. And similarly, for gusset plate, we have this expression where I need to calculate A, which is basically 0.05, and that you can find out from this expression. Okay, and then cos theta, theta is 60 degree, which is given, and then you can find out this TG value, which is 0.02798 meter. Okay. Now, what is this F? This F, here we have considered allowable stress of horizontal plate, and here it is allowable stress of gusset plate. In this case, these both values are equal, otherwise we need to consider accordingly. Next step I am having is to determine the area of cross section of the channel column for sectional modulus of 200 centimeter cube. Okay, and we need to suggest the suitable column for the bracket. Okay. So, this is the expression to calculate the cross sectional area of column, where x is the cross sectional area of column. All these parameters we have already discussed in the last lecture. Okay. So, considering all these parameters, where F is the allowable stress of column. Okay. So, that you need to consider, and solving this equation equating to 1, because that would be the extreme condition, and accordingly I can find x as 47.29 centimeter square. So, as cross sectional area of the column comes as 47.29 centimeter square, I have to choose the column which is higher than this area. Okay. So, for that purpose I have to see the table of channel, which is basically table C3 in BC Bhattacharya book. So, here you see 47.29 was the minimum area. So, here what I can suggest? I can suggest this one, or I can suggest this one, which is greater than 47 centimeter square. So, either ISLC 350 can be considered as suitable column, or ISMC 350 can be considered as suitable column. So, that depends on us that which column I should use, but both column I can use easily. Now, here I am having second example, which is on design of saddle, and in this example I need to design a saddle support for horizontal drum, which is designed for internal pressure 2.1 meganewton per meter square, internal radius 1.2 meter is given, tangent to tangent length is 15, depth of the disc head, that is capital H, as 0.4 meter is given. Allowable stress, yield point of the material are given as this: corrosion allowance 0, joint efficiency factor 1, modulus of elasticity is given, and total load on each saddle, which is given over here as 1.4 meganewton, contact angle is 120. So, what I need to find is check if the following assumed saddle design data, that is A by R equal to 0.6 and B equal to 0.5 meter, satisfy all design stress conditions. If not, find the new values of A by R and B which satisfy all design stress conditions. So, let us start the solution of this. Here basically in saddle I need to compute different stresses, and that should be satisfied with the permissible values. Okay. So, let us start that. So here I am having all parameters which we have just discussed, and A by R is given as 0.6. So from that we can compute A, which is basically 0.72, and it is greater than R by 2, because this condition I need to use. So here A is greater than R by 2. B is given as 0.5 meter, which is the width of the saddle. Okay, so all parameters I guess you understand. W1, that is weight on each saddle, is given as 1.4 mega Newton. M1 and M2 I can find out directly through the expression, and M1 comes out as 4.119 mega Newton meter and M2 as minus 0.0236 mega Newton meter. So considering these moments, we will calculate all stresses, but these stresses will also require thickness of shell, and therefore we can compute minimum thickness of shell using usual expression. And here if you remember, 1.2 meter R is given, which is internal radius, so internal diameter would be 2.4. okay. So that we have used over here, and therefore this minus sign appears, and minimum thickness comes as 16.92 mm. Considering these value, we can find out F1 as 20.656, F1 dash as 128.28, okay, F2 as 71.58, considering K1 as 0.107, and F2 dash comes as 76.07, considering K2 as 0.192. Now from where this K1 and K2 comes, if you see here I am having this K1 where this condition will be applicable, A is greater than R by 2, and this K2 is given where A is greater than R by 2. So K1 0.107 corresponding to 120 degree angle, and K2 comes as 0.192. So considering these value, we can find F2 and F2 dash. Now you see this should be satisfied with Fj, so that should be less than or equal to 150 mega Newton per meter square. So all conditions are well satisfied. And further we have to find out tangential shearing stress, and that case comes as when A is greater than R by 2. So we will use this expression where K3 is 1.171, and that is given by this expression where K3 I am considering, here I have different condition. I have taken this condition, that is shell unstiffened by rings, where no rings is provided. If rings will be provided, it will be given in the problem. So corresponding to 120, K3 value comes as 1.171. So considering K3 as this, we can find out Q, which is coming out as this, and this should be lower than 0.8 into F. So it is well satisfying the condition. Next we have the F3 value, and F3 will be given as K5W1 by T B plus 10 T, and K5 you can see as 0.76, and here you can see K5 as 0.76 from this table corresponding to 120 degree, and considering these points, K3 comes as 94.108, which is well satisfying the condition, that is it is less than 120 mega Newton per meter square. And further we will calculate F4. For this we need K6, and K6 is given as 0.18. So further you see this table where Kc we can see figure or table 10.5 from book, okay, and book is B.C. Bhattacharya book. When A by R is 0.6, okay, and theta is 120, so corresponding value of K6 is coming as 0.018. This is the table from book, okay. So considering this, you can calculate F4, which is coming as minus 163.305. Now we have the horizontal component of all radial forces, because till now we have discussed, we have computed stresses due to internal pressure as well as due to saddle in shell. Now we need to check for saddle strength. and for this we have to calculate F4, for which I need K9, and K9 is given as 0.204 in this table. Okay. Considering that value, we can find F as 0.2856, and then this condition we need to satisfy, which is this expression comes as 1.428 and this expression comes as 100 mega Newton per meter square. So, it is well below the permissible limit. So, in this way we can design the bracket as well as saddle support, and here we have some of the references to study the topic, and here we have summary of the video and this summary of lecture 1 as well as lecture 2, which is on design of support, and it goes as: supports for vertical and horizontal pressure vessels are discussed. Design of bracket or lug support for vertical pressure vessel is described. Design of saddle support for horizontal pressure vessel is discussed, and then few worked example we have discussed with detailed solution. And that's all for now. Thank you.